Hey guys, I hope all is well. I was gonna send you a little homework help video here for homework 3.2, which has chapter 14.2, 14.3, and 14.5 homework on it right here. The theme of this video will be making your life easier with Excel's data analysis tool pack. Please try to start using this tool. You'll definitely have to by the end of the semester. So if you've been avoiding it, now is a really good time to start using it. Because as you'll see in these homework sets, basically just applying it once using the regression option is going to produce all of the answers we need for most of the homeworks. So let's start with an example from 14.2 homework. So here's a little preview of that excitement, maybe. And so this one has scatter plots, which are similar to what I've been doing in the videos. So let me see here which one. I think I'm just going to go for the first one because they're all very similar, and I can show you a little trick. If we copy this type of data into Excel, so I'm just doing number 1 from the 14.2 homework assignment. This will paste nicely into Excel using a regular paste, but when we're doing regression in the data analysis tool pack, we want to actually transpose our data so that we're in columns. So the way to do that is you want to paste it for the first time as rows into Excel, but then after that, paste special. And in a Mac down here, it says transpose. But if you do paste special on a Windows machine, there will also be an option somewhere that says transpose. And if we do that, we get our data in columns. So that's the first thing we want to do because the data analysis tool pack is going to expect our data in columns. So in this problem, we're estimating an equation between x and y right here. So if I do data analysis, and regression is just alphabetical order menu, so it's right above those t-test ones we were doing last section. Push OK. Now let's put our x, or our y range goes first. I like to always include labels just like before, so I highlight all of that column of data. X range, I'm going to include labels. So there we go. And now output range, where do we want to put you? Let's just go right there. I guess that's where it was before. And so this gives us a ton of information, which we looked at in the previous videos. But I just wanted to show you guys how this can help us with the question. This question also has a scatter plot part. So maybe it would be a good idea to also just throw our scatter plot on there, and that'll help us with that problem. It always just names it the dependent variable. You should change the name of scatter plots if it just names it like that. So let's take a look. So right away we see this positive looking relationship. It looks like that one right there. We can kind of check, is this point down here below 3? Yep, that looks like it's in about the right spot. So I'm assuming that's our answer for the scatter plot. That one, last one, might be worth checking too. I will leave that to you. And so this one, same idea, you're just drawing a line through it, which you know how to do. If we right click on here and add a trend line, then we can see the line through our data. And now we can probably do an even easier job of finding which one of these graphs is the one that's associated. Now this is where I really wanted to get with starting to use the data analysis tool pack, because these equations that Excel gives you obviously work. This is the equation that we use if we are estimating the slope right here. And this is the equation we would use after we figured out the slope number. We would be able to use this equation to get our estimate of the intercept. Now, you can do that, but notice that the data analysis toolpack gives us those numbers. Here's our slope right here. So that's the 2.4. So that's the slope. So maybe just write slope here. It will always label the slopes with the name of the independent variable. The reason for that is that in our future, we're going to start putting many independent variables in the same regression. So that's going to be a nice feature in the future. But just so you should know what these two numbers are, it always gives us the intercept first, and then it gives us the slope. So you actually don't need to necessarily do the equations to do this homework because the data analysis Toolpak will give them to you as long as the problem gives you the data. And as far as I can tell, all of these section problems give you the data. So now use the estimated regression equation to predict the value of y when x equals 2. Well, anytime we have an equation, if we have x is 2, then we could just plug in, we'll call it y hat because it's like our estimated value of y. And so we're still using that hat idea. Remember, before we were using like x bar or p hat, we use hat to represent estimates. So if I have an equation which involves an intercept and a slope, and I have an x value, then I can predict my y value by saying, okay, I'm going to do the intercept plus the slope multiplied by the x value. Because that's what this equation says, that's the relationship between x and y. So that's how I might get E right there. So this was the intercept, by the way. So we had the intercept, which was part of D. And so they actually want you to write the entire equation right there for y hat. Or so for y hat, I guess they want you to just type the entire equation into this one, but let's take a look at a D. So yeah, they want you to write 0.8 plus 2.4 times x, because if we wrote this equation out, that's what it would be, right? This equation says y equals 0.8 plus 2.4x. That's how we would write that equation. In algebra class, you probably flip the order. In statistics, we always write the intercept first. So that's an example of how really quickly, notice, we got the answers using the data analysis Toolpak because they gave us this data. So I just wanted to show you how quickly you can do some of these if you use this. Otherwise, you have to use the formulas. Now, these ones, the section 14.2 homework is pretty chill, but using this data analysis Toolpak on these 14.3 and 14.5 will save you even more time. So let's take a look at 14.3 really quick. So similar problem right here. So let's just do the first one because all these are similar. Notice that we actually have the same equation. Let's see, did they give us exactly the same data? Maybe we don't even have to do anything. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 7, 6. Oh no, they didn't give us exactly the same data. So let's label this. This was 14.2, number 1. Now we're going to do 14.3, number 1. And so I'm going to go ahead and copy this data in, paste, zoom in on that a little bit. And now, of course, we want it in columns like I did last time. Paste special transpose. We delete these guys. So there's our data in columns. Data analysis. And this will preload. Notice it's going to preload what we did last time, so it's going to be pretty close. So yep, y is b to b6, and x is a to a6. I included labels. Output range is D1, that looks fine. So similar information, we actually got exactly the same slope because apparently they're picking these numbers to make sure we get the same slope and intercept, but this change in numbers could have changed some of these other statistics, so I didn't want to risk just being like, oh, they probably made everything the same. Now, a big thing here, the main thing you're going to have to think about is that the book uses slightly different terminology than the data analysis Toolpak. So at first here, the trickiest part of applying the data analysis Toolpak is probably just going to be getting used to the differences in terminology. So let's take a look here. The estimated regression equation is 0.8 plus 2.4x. Here we can confirm that, make sure that we highlighted the right data, for example. So that is consistent. This intercept and this slope are definitely consistent with what they're showing us here, right? So that's a kind of a nice check we might do. Now it says to compute the sum of squared errors, sum of squared total, and sum of square regression using equations SSE, SST, yada, yada, yada. Now you could totally apply those equations. We'd want to figure out y hat and do them by hand, but these are another thing that the data analysis in Toolpak includes for us. So the way Excel labels those, though, is SS is right here, so sum of squares. This is going to be sum of squares regression is what Excel calls it. And so this is going to be SSE in Excel, though. So we have to get a little bit used to this. I like to start with the total. Sum of squares total is the same in both cases. So this is like SST. And that will always be the biggest number because that's the largest deviations. That's the total deviations between y and y bar. And then the question is, well, how much of that do we account for when we use our regression? So this is SSR is the amount we account for. So Excel is calling that regression. That's how much of the variation in y is being explained by our regression. Okay? And then this is going to be SSE, sum of squares error, but Excel calls those residuals. So SSE is the amount we're not explaining with the regression. Now, it also tells us that the r squared, I guess it doesn't give us the formula right here, but the r squared should be equal to the sum of squares regression divided by the sum of squares total. And notice I just did a check because Excel calculates that for us anyway. So now when we go into these questions, it's just mainly the hard part is going to be making sure you label these correct. This order will be always the same. So if you come and watch this video, you'll be good to go because I just labeled them for you. And so SSE is the first one they want. That's 6.4. SST is 64. SSR is 57.6. Now here is compute the r squared. We just did it by hand because the r squared is the percentage of variation that your estimated regression explains in y. Because that's kind of our goal of regression, is explaining or predicting y. So it'd be good to know how much of y can be explained by this equation that I estimated. This says 90% of the variation in y can be explained by x, or this regression equation. This is the total amount right here of variation when we just like add it all up. But those are numbers we don't really like because it's hard to understand what that means without even knowing what the units of x and y are. Like that could be a huge number or a tiny number. But once we convert it to a percentage, it's always an apples to apples comparison, because now we can say 90% of the variation in y is explained by variation in x. Or another way to say that is 90% of variation in y is explained by my regression equation. So this would be 0.9 right here. Then that one's just asking you to compare that to this other number. The sample correlation coefficient right here, that's going to actually just equal the square root of r squared. This is your correlation coefficient that you looked at last semester. Oh, check it out. It turns out that Excel also produces that number, but it calls it, of course, something else. So this is what Excel, that's where they put the correlation coefficient, but they call that the multiple r. So notice, all I did was take the square root of r squared, and I got this number. So that's another number that I didn't really need to make any calculations for this problem. All of them are displayed in the data analysis Toolpak. It's just a matter of recognizing where to find them. So again, make sure to use the data analysis Toolpak in this problem. So here's our SSE. We just want to check to make sure. So our SSE is 6.4. That's what we had right there, SSE. SST was 64, sum of squares total. That's right there. R squared is 0.9. Oh yeah, SSR right here is 57.6. And notice that what they're showing that equation is that if I did the total sum of squares minus what I didn't explain, then I'd get back what I did explain. So these two numbers are like, this is what you can explain with your regression. This is what you can't explain with your regression. So these two numbers have to add up to the total. And now they show that the correlation coefficient is just the square root of 0.9 or 0.949, which we showed right here. Or we saw that Excel already also displays that number, but they call it the multiple R, because this said multiple R before I changed it to correlation coefficient. So again, the data analysis Toolpak produces basically all of these numbers for you. It's just a matter of figuring out where they are. How are you going to do that? You're going to watch this video. All right, let's check another one out. So the last assignment from this section is going to be 14.5. And same deal, basically they're just going to ask us for more of those numbers from that same homework. Let's see, did they actually give us the same numbers this time? 3, 8, 5, 12, 14. 3, 8, 4, 12, 13. Oh, it's close. Okay. So we're going to do 14.5 number 1 now. I'm going to copy this data in. Paste. Copy it again. Paste special. Transpose, delete these, and then hopefully my data analysis Toolpak will be set up with that same range of data, which I think it will, but let's make sure. Yep. Labels, D1 still looks good. So here's our results from this data set. Probably gave us the same. Oops, our slope and our intercept changed a little bit that time. So now let's take a look. Now they want the mean square error, so MSE. And so that says it's going to be that SSE divided by n minus 2. So remember, what did we have over here? This was SSE, this was SST, and this was SSR. Notice observations right here. This is n. So they say that this MSE thing is going to be equal to SSE, that's that number, so that was similar to from the last spreadsheet, right? Divided by n minus 2. So that's the formula they give us right here. Notice that is right there. So they're giving us that number in Excel too. Now that's just in the MS column. This is basically taking the averages of these numbers. And so there's our 5.866, which we just calculated with the formula they gave us, but now we see that Excel already gives us that number too. Let's compute the standard error. So that's going to be the square root of what we just computed. So this is the standard error of estimate is what they refer to this one as in the book. It's going to be complicated to keep our heads around which of these different standard errors, because in the next one they're going to call it a standard deviation. I'm mainly going to care about the main 3 numbers for this chapter that I showed you in the last video, which were the R squared, the slope, and the slope's p-value. So really I want you to just hammer through these. I'm not going to ask for tons of interpretations about all of these numbers they're asked for. It's kind of just a nice introduction, like, hey, every single number they're showing us here has meaning. and you won't have to go through this too many times. And it looks like they give us most of the formulas anyway, so let's check this one out. SSE divided by n minus 2, that's what we calculated right here. So we just need to take the square root of that number. 2.422, that is right here, so they give us that number too. So that's called the standard error of the estimate right there. So it's kind of talking about the standard error of the entire regression equation is the way that you can think about that. Now compute the estimated standard deviation B1 using this. Now that number, it turns out, is just the standard error of the estimate. So when they say, remember B1 is our slope estimate, and then it wants the standard deviation of that. So just going back to what we've been doing for the semester, anytime we estimate a number with data and then look at that estimate's standard deviation, we refer to that as a standard error in statistics. So they're saying the standard deviation of your slope estimate, what they're talking about right there is the standard error of the slope estimate. And check it out, it's right here, 0.766. So that is the one number you should be looking for when they ask you for the standard error or standard deviation of the slope estimate. So standard deviation of B1, because B1, remember, is how we label our slope estimate. So then find the p-value, and they're talking about the p-value. So now we're testing the following hypothesis. This is about the population slope. Here's our slope estimate. So this is exactly the same relationship between x bar and mu, except now we have B1 sample slope, beta 1 population slope. So find the value of the test statistic, round your answer to 3 decimal places. Our test statistic, t, right there. That's the test statistic you want. What's the p-value? It's right there. Because now we're doing a hypothesis test specifically on this slope number, right? That's why we're looking at this standard error, this t-stat, this p-value. Okay, so then you can reject, same rejection rules as before. And so now there's this horrible table of stuff, but which would be really, really harsh to calculate these by hand. I'm telling you, it would be horrible to calculate these by hand. But notice, I'm feeling like I'm seeing a pattern here. Regression error total, regression residual total, but residual basically is a synonym for error. DF, degrees of freedom. SS, sum of squares. MS, mean square. F, significance F, this is the p-value associated with F. So just real quick on what F is, notice in this problem that this p-value is exactly the same as this p-value. The F statistic is kind of like, is your overall model significant? Like, does your regression equation that you estimated have statistical meaning? Well, in this case, our entire regression is just having one independent variable. So asking if our entire regression has statistical meaning is the same thing as asking if this one independent variable has statistical meaning in this case. And that's why we get exactly the same p-value. When we start adding additional independent variables in chapter 15, that's when we'll start to see our F statistic deviate from our p-value. So the value of the test statistic, that's going to be this F value right here. And then the p-value, of course, again, you're just going to repeat down this p-value. And then these are the similar interpretations. Same exact thing as chapter 9 and 10. If your p-value is less than the significance level, then you'll reject. If it's greater than the significance level, you'll fail to reject the null hypothesis, and so on. All right, so reach out to me and let me know if you have any questions about this. Please do not hesitate to use the data analysis Toolpak on this homework. Notice how quickly we just did those problems. It's been about 25 minutes with me explaining them, probably telling you stuff you don't necessarily need to know. But you can do all of this homework quickly if you use the data analysis toolpak. All right? Talk to you guys later. Bye bye.